Hey there students, Mr. Pugh here. In our video today, we're going to be going through an overview of our next lab dealing with our smart cards, Lab 2D Smart Speeds. Now, the numbering system may change a little bit year to year. Sometimes we add and take away some labs. So for the year you're looking at, this may not be 2D, but we are going to be titling this lab Smart Speeds. And our focus for our lab here, we're going to be looking at checking some of our kinematic equations along with our smart card. Now, you will want to make sure you can access the lab sheet, as that's going to give you a bit of a guide on where we're going with the lab. So make sure to navigate over to Canvas, and you should be able to access our lab sheet there, likely on the Week at a Glance page or under the Assignments tab. So if you need to pause for a moment and go and do that, you'll want to make sure you have this up there. You likely won't be able to see the exact document very clearly from the video, so you'll want to make sure you have access to the document. So let's talk a bit about where we're going with our lab for today. Our lab here, as I mentioned, is going to deal with the concept of kinematics. More specifically, we're going to be using our smart cards to look at the velocity of our cards, and then using that to analyze a few students' different predictions and opinions. So here, here's the context that we're looking at. What we're going to be doing with our smart card is propping it up on one end with a book and releasing it from rest to travel down the track and hit the wall. And what we're going to try and do is we're going to try and make a prediction on what we think our final velocity would be. We're going to define the final point as the point just before colliding with the wall. And once the card hits the wall, there's going to be a force there that's going to affect its motion. And so that's going to be a point in which our acceleration is no longer constant, if you remember from our kinematic equations. So we're just going to look at the card as it goes from rest, down the track, and then just before it hits the wall. We're going to do this both with one book propped up on the track, or underneath the track, and then as well we'll do this with two books. We'll start with one and then add our second in. And in doing that, what we're going to be doing is checking the predictions made by two different students. So student A, if you're referencing the document, makes the prediction that the velocity of the card can be found by taking the distance the card travels, and we can measure that actually using our smart card software, the distance the card travels divided by the time it takes to travel that distance. That is student A's prediction. Velocity is distance over time. Now student B, and he says that they're cautioned that distance divided by time could be misleading, and they recommend using the fourth kinematic equation in order to check what's going on with the velocity. So what we're going to do here is we're actually going to collect some data using the smart cards, and then we're going to make some predictions on velocity based on what the students tell us, and then we'll see which student's prediction actually matches what's happening in the physical world. And so again, to be clear, we've got these two different students, A and B. They each have a prediction on how to find the velocity. We're going to use the smart cards to collect some data. We'll make predictions using what the students have to say, and then we'll check and see whose prediction is more accurate with what's happening there in the real world. Now, if you're in class, you'll be doing this here in the classroom with your own smart card and your own setup. If you're doing things remotely, I'm actually here in a moment going to be walking through a bit of a sample procedure on how to do this so you can see what the data looks like and how things actually shake out. Okay? Hopefully that gives us a bit of an overview of where we're going to go. If you're doing this in class, you can now start working on collecting your data and getting your things set up. If you're doing things remotely, stick around and we'll go over what the procedure looks like here together. Okay, so now that we've done a bit of an overview on where we're going to go, we're actually going to go through and complete the lab here together so you all can get the data that you need to be able to make your predictions. Okay, so one thing that we're going to try and make sure we do each time is we're going to try and make sure that our initial velocity is 0 meters per second. Okay? That is one thing that we're going to try to make sure we do each time we collect our data. Now we're going to do that by making sure our card is at rest when we hit collect. Now I've got my Chromebook over here, and hopefully in the corner of the screen, or at least in some area on the screen, I'm going to try, in fact I may actually come over here to this side, that way I can try and put the actual graphs up here on the side of the screen so you all can see them. But I'm going to actually go ahead and run through trials. Now what I want to do is I want to get my cart on the top of the track. Now in the bottom right corner of my screen, I see where my position sensor is giving me a reading on position. What I'm going to do is I'm going to go ahead and zero out my position so that it's reading that my initial position is 0 meters, okay? Now, what I'm going to do from there is I'm going to go ahead and hit collect, and then I'm going to run the trial and see what our numbers look like. Here we go. 3, 2, 1, go. Okay, I'll let it go until it clearly hits the wall, and then I'll hit stop. Okay, so the point I want to look at is here, right before our velocity goes to 0. So I want to look at this point right before our velocity begins to go down. So right here, it's looking like our final position is 0.897 meters. Sorry about that. 0.897 meters. And my initial time we'll say is 0 seconds. Our final time, I can see that down here actually on my graph, 2.62 seconds. Okay. Now, I'm not going to get the final velocity yet. I'm going to actually use the students' predictions, or their opinions, I should say, to make a prediction, and then we'll check that. Okay, so I've done this with one book. Now, I'm going to run this with 2 books. Okay? So here we go. In fact, I may actually, for now, go ahead and turn my velocity graph off. So now we've got 2 books. I'm going to bring our cart back up to the top of the track and make sure we're position 0. I can see that down in the corner, position 0. And here we go. 3, 2, 1, collect. Now you'll notice there, it actually didn't start collecting data when the position was at 0, so I'm going to run this trial again. You want to make sure it does actually collect data at time 0 being position 0. So I'm going to try that one more time. 3, 2, 1, collect. There we go. Okay, so I've got there. It looks like the cart begins moving, and okay, so it looks like it begins moving about right here, and that would be 0.016, so very close to 0. And our final position there, in fact, I actually might need my graph back on. There we go. So I want to see where the velocity begins to go down. That's going to be at 2.1 seconds. And it looks like we started at 0.42. So 2.1 seconds. This was 0.4, a little bit messy there. 0.42 seconds. And it looks like our initial position was 0.014. Again, very close to 0, which is good. And then my final position, when my velocity began to decrease, we're looking at 0.886 meters. Now, one thing I'm noticing is I was assuming my time was 0, my initial position was 0. I'm going to come back real quick to data set 1. I'm going to turn on position. And then for my velocity graph, I'm going to turn on velocity of data set 1. Okay, so it looks like here was my final position, 0.897, and that was at 2.62. But it looks like we didn't actually begin until about here when our velocity was increasing. And that was in fact at 0.26 seconds was when the card actually began being released. So I'm going to go with 0.26 seconds, just so I'm getting, hopefully, a pretty accurate reading on the time. I believe so. Sure, 0.26, and I go to about 2.62. Now you may notice it's taking more time to get down the track when it's angled up just with one book than it does with 2 books. That's likely because it's going to be faster with 2 books. Okay, so now that I have my data, and this is what you can use to be able to complete the analysis there on your own. Okay? I do want to make sure we're clear. Our goal here in doing this is to make a prediction on the final velocity using what the students predict. So on the second page of the lab, we're going to make a prediction based on each of the students, we're going to make a prediction based on each of the students' opinions, and then we're going to check that with the actual value from the students. The actual value from the software system. So what I want you all to do is to take that data that we just collected, use that, make your predictions based on what each student believes, and then we'll check those numbers with what actually shakes out. Okay? I will be loading up another video later on for you all to see what those predictions would look like based on the sample data. But for now, I want you to take that information, make your predictions, and you can come check in later to see what the actual analysis looks like. Hopefully that gets you going here with what we're doing in Lab 2D. As always, if you have questions, feel free to let me know. Other than that, good luck. Okay, so now that we have our data, what we're going to be doing is walking through a bit of the analysis so you can check your results. So student 1's method, very generally, student 1 believed that the velocity was simply distance traveled over time. So what I'm going to do for each of these predictions for student A is just take our total distance divided by our total time. So coming back to our data, real quick, our distance traveled is going to be, well, delta x is final minus initial. So for student A, I would take final minus initial, so 0.897 minus 0, divided by our total time. So this was our ending time and our starting time, so this would be 0.897, and then divided by 2.62 minus 0.26. So there I get a final velocity, according to student A, of 0.38 meters per second. That's what student A would predict the final velocity to be. Now, for 2 books, we'll go with our total distance over our total time. So delta x there, again, is going to be final minus initial. So I'll take 0.866 minus 0.014, okay, and then divide by our total time. So that's going to be final minus initial, so 2.1 minus 0.42. Okay, so 0.507, so I'm going to say 0.852 over 0.507, and I get a final velocity of 1.68. So, for student A, these are the predictions we have on our final velocity, using student A's opinion. Now, student B says we should use the 4th kinematic equation. I'm going to show you all that real quick. Kinematic equation 4 is delta x is equal to 1/2 v0 plus v1 times t. Okay, now in both of these experiments, our initial velocity was basically 0. If I look back at my data, I'm seeing that the initial velocity was effectively 0. So what I can do with this equation is, this term goes to 0. So delta x is equal to 1/2 multiplied by v1 times t. So to find my final velocity, I want to get that v1 term by itself. I would actually multiply by 2 to get rid of the 1/2, and then divide by t, so I get that my final velocity is 2 multiplied by my displacement divided by divided by t. So let's now use this equation to find v1 using student B's prediction. I might have been saying student 2, I'm sorry if that's the case. It is A and B, sometimes I get that confused and say 1 and 2. So this would be the equation for student B's predictions. So I'm going to come back. Student 2 is saying that our final velocity is 2 times the displacement over time. So for student B, I'm going to use try one with one book. So 2 times delta x, 2 multiplied by 0.897, divided by our total time, so that's our final time minus the initial time, so 0.76 meters per second. So student B would say this is 0.76 meters per second. You'll notice that's double the prediction made by student A. Look at the equations there. Student A is saying it's just distance over time. Student B is saying I use my kinematic equation, and when I do the algebra to isolate V1, I end up getting 2 times delta x over time. So it may be the case that student B's prediction is double student A's. Looks like that's what it seems to be. Okay, so come back to our 2-book trial. I would take my displacement, so 0.886 minus 0.014. So it's 2 times that delta x divided by our total time, 2.1 minus 0.42. And I get 1.03. Is that right? I think so. I made a bit of a mistake here. So if you're watching the video and you might have seen a mistake there, this is actually 0.507 meters per second. Made a bit of a mistake there, so my apologies on that. But that does seem to fit our pattern a little bit better, okay? So we're seeing that student 2's prediction, or student B's prediction, is kind of double what student A's prediction is based on the equations that we're using. Okay, so now the goal is, what's real? We've made a prediction based on each student's opinion. What actually is the final velocity of the cart right before it hits the wall? So let's come back to what we see on Vernier, okay? And I'm seeing, and I'll probably have my screenshots in here. I've got trial 1. Let's go final velocity. So trial 1, we're seeing a final velocity of 0.73. Looks like about 0.735, 0.74. So actual one book, we see about 0.74 meters per second. That appears to be close to the student B's prediction. And then we'll throw on our 2-book trial. And there we see our final velocity about 1.03. So 2 books, we see about 1.03 meters per second, which actually is pretty well in line with student B's predictions. So what is that telling us? Well, the data is telling us now that student B's prediction is accurate. What student A is saying is that our velocity is just distance over time. That approach does work when we have when we have a constant speed. If we have no acceleration, that approach works, distance divided by time. However, anytime our object is speeding up or slowing down, we have to account for that acceleration by using one of our kinematic equations. So it's very important for us to see that the best way to solve for things like velocities, times, accelerations, any of those kinematic variables, is to always go back to using our kinematic equations. That little shortcut, distance over time, only works in very specific situations where our acceleration is 0. Actually, the best way to find what's going on with kinematics is to make sure we use our equations and not just try and use some of those shortcuts. Okay? So hopefully that gets us going here with what we're doing in Lab 2D. Okay? As always, if you have questions, feel free to let me know, but you now should have the information that you need to be able to fill out and complete the lab remotely if that is something that you're needing to do. And as always, if you have questions, please let me know. Other than that, good luck.